Hi and welcome to our first chemistry video of our Chemistry 4DS. We're going to take a quick look back through the subatomic particles involved with Bohr diagrams, and we're going to create ionic compounds. We'll use Bohr diagrams for our first one, and then we'll kind of start to zero in on Lewis dot diagrams and using ions from our ion chart. With potassium, we find that on the far left side of the periodic table in group 1. It's got 19 protons. So we'll put 19 protons in the nucleus. 2 electrons in the next energy level. And then subsequent ones are going to have 8 max. So we kind of enter them in here, like kind of 3, 6, 9, 12, as if you're going around a clock. And we've got to add up all these electrons until they get up to 19. So we had 2 and 8's 10, plus 8's 18. So we need a 4th energy level, and that energy level is going to have just a single electron in it. Chlorine, on the other hand, is on the right side, far right side. It's in group 7. And so it has 17 protons. That's the atomic number for chlorine. So 2, and then again 8 going around. And when it comes down to the very last level, you know, we can have one. So we've got 10 so far, 11, 12, 13, 14, 15, 16. We'll throw the 17th one up there. So looking here at potassium, we see that there's just one single electron in the valence shell. When we look at chlorine, we see that there's a total of 7 valence electrons, and valence means the outermost energy level. So looking at potassium, we know it wants to observe the octet rule. It wants to have a full valence shell. It can either somehow get 7 electrons to get a full 8, or it can give away. And so what we're going to see is when potassium combines with chlorine, this electron will be given away. And on the other side, chlorine, with 7 valence electrons, just needs one more in order to have a full valence shell. So this guy's going to receive 1 electron. So potassium will lose 1 electron, and chlorine will gain 1 electron. This forms a charged particle. So overall, we have 19 protons, and there's only 18 electrons left over. So the net then is we're up 1 proton. So we have a +1 for the potassium. Whereas chlorine had 17 protons, and it will gain 1 electron, so it's going to have 18 electrons. So it's up 1 electron. So it'll be a charged particle, form a -1 ion. All in all, the ratio is 1 potassium to 1 chloride. And so if we're to make a chemical formula, we would have like kind of invisible ones down here. 1 potassium to 1 chloride. But we don't normally show that, so we see the potassium chloride. In terms of creating a Lewis diagram, all these dots, they start to get really, really nasty after 20. Basically, calcium's our last friendly one. And then into the transition metals, it gets weird. So we only represent the outermost valence. So for potassium, we would use the symbol in the center. We don't write the protons anymore. And we just write the single electron. So that's the Lewis dot diagram. For potassium. For chlorine, we're going to use the symbol in the center, and then we're going to show all 7 of those. You know, if you want to, again, do it like that, then you can see how this electron can be lost, and over here it can be received. And the whole idea is that they're trying to become like their last noble gas. So let's take a look at another set of elements, and we'll just use the Lewis dot diagram for that. So barium is in our group 2 elements. So we'll put our symbol down and put 2 electrons representing the 2 that are in its outermost valence shell. Chloride, we know, chlorine, I should say. That was miswriting, but chlorine has 7 valence electrons. That's characteristic of group 7. And now if we're going to create an ionic compound where we're gaining and losing electrons, we've got chlorine, which we know is highly reactive. It only needs 1 more electron. And so if barium's coming around, chlorine is going to ask barium, hey, give me that electron. And barium will give that up, but then barium will be left with 1 more electron, and it won't like to be that unstable. It would rather have lose all the electrons in its valence shell or not at all. So another chlorine is going to have to come around. In order to receive the second electron from barium. And so when we want to write out this scenario where for every 1 barium, it's reacting with 2 chlorines, when we write out the formula, you know, I'm not going to write the little 1, but it means that there's just 1 single one there. And then for the chlorine, I'm going to put a 2 there. So this 2 is our subscript. And that's representing that 1 to 2 relationship, that for every 1 barium, we need 2 chlorines in order to react. And then I just wanted to illustrate using the crisscross formula. So if we grabbed our ions either from the periodic table, because if we go to barium, barium is going to have a +2+ ion beside it. Chlorine will show a -1, and we know that it's going to have a -1 charge when it gains those electrons. And we can crisscross this. Take the combining capacities, crisscross them, and they become the subscripts. So we end up having BaCl2. So both ways work. You know, it's typical for folks to understand things and visualize things in this way, you know, where you're visualizing the transfer of electrons, whereas like in practice, maybe we're just grabbing our combining capacities off of our periodic table and using them to crisscross to complete the formula. So I want to show you one sort of exception to that rule. And that's with aluminum nitride. So, again, we'll start off with Lewis, just so that we can see what's happening here. Aluminum has 3 electrons that it wants to give away. We know that because it forms a 3+ ion. Nitride, or is just a regular nitrogen, and nitrogen itself has 5. It's in group 5. So 1, 2, 3, 4, 5. So how can these guys form an ionic compound by losing and gaining electrons? well, nitrogen's saying, give me 3. If you give me 3, I'm going to have 8. And aluminum's like, okay, I actually happen to have 3. You can have them all. And the relationship is 1-to-1. For every 1 aluminum, it just matches perfect. It's like a puzzle piece, just fitting perfectly with the nitrogen. Now, if we went to crisscross, and we did this crisscross, we're going to get a bit of a problem because we actually get this. And so what we have to keep in mind when we do crisscross is that we have to reduce, if possible. And so let's say you had 2 and 2, or 2 and 4, or 3 and 6, something like that. If there's any way, to reduce, so in this case here I divided by 3, then you want to, because this is representing this 1-to-1 relationship. So in general, crisscross will absolutely work to create your ionic compounds, but just really be careful about the ones where you end up having to reduce.